Hello, everyone. Good morning. Let's continue with derivative. Previously, we talked about partial derivatives. Now, today we're going to continue with so-called higher order partial derivatives. Well, let's start with an example. What I really mean is that sometimes we want to take derivatives more than once. So for example, we might have a function, say f, from R2 to R. A function with two variables. Okay, we can show the variables with x and y. So for example, suppose the function is x squared y plus 3y squared. Now, I can take derivative of the function with respect to x. It simply means I should assume y is a constant. This is another notation for derivative with respect to x. I'm not sure if I introduced this notation too or not. I think no. This is another derivative, another notation for derivative with respect to x, or f with f sub x. They all mean derivative with respect to x. And it would be here 2xy, for example. Now, the point is that we can take a second derivative with respect to x. So we have computed the derivative with respect to x, which is 2xy. We can take derivative with respect to x again. So this is the notation we use. Take derivative with respect to x again, partial derivative with respect to x again, which here would be 2y. So different notations we use for this thing are, well, one of them is this. It means take the derivative with respect to x of the derivative of the function with respect to x, which is here, say 2y. We also sometimes use this notation, partial squared of f over partial x squared. Sometimes we use this notation, f sub x x. That all of these things mean second derivative with respect to x. We can do the same thing with respect to y. So again, for example, if our function f of x and y is equal to x y cubed plus y squared, we can compute the derivative of the function with respect to y, which is, this is one notation for that. The other notation is partial f, partial y. The other notation is f sub y. Here, the derivative with respect to y is 3x y squared plus y. We can take the second derivative with respect to y, which means we should take derivative with respect to y from the derivative itself. So the notations we use are derivative with respect to y of derivative of f with respect to y. We might use the second derivative, partial squared of f over 2y. Yes, thank you. Partial y squared. We might use this notation, partial y yf. It means second derivative of f, or partial squared of y. or f index y. They all mean second derivative with respect to y, which in this case is 6xy plus 2. Now, we might have so-called mixed derivatives. It means we might take derivative with respect to x, then we might take derivative with respect to y. So again, let's say f of x and y is x cubed y squared plus x squared y. I might first take derivative of the function with respect to x. So here would be 3x squared y squared plus 2xy. And then take derivative with respect to y of that results. So here it's going to be 6x squared y plus 2x. The other notations I might use here is partial square root of f, partial y, partial x, or partial y, partial x of f, or f sub x, y. It's a little tricky here. The order here is different with the order here. So here, the first letter here means we should take first derivative with respect to x. Then we should take derivative with respect to y. First derivative with respect to x, then derivative with respect to y. But here it means we should take derivative with respect to x first and then with respect to y. But the good thing is that it usually, in good situations, it really doesn't matter. What do I mean by that? Well, look at the result here, 6x squared y plus 2x. What if I first take derivative with respect to y and then take derivative with respect to x? What if I change the order I'm taking derivative? So if I first take derivative with respect to y from this function here, what I would get is 2x cubed y plus x squared. Now, if I take derivative with respect to x, what I'm going to get is 6x squared y plus 2x. So as you can see, what I got here is equal to what I got before. So it seems, at least in this case, if I take derivative of f with respect to x and then take derivative of that with respect to y, it is equal to taking derivative of f with respect to y and then taking derivative with respect to x. Yes, it's good to, well, yeah, you should know the derivative, the notations. Part of the math is the notations we use. Yes, I can go back for a second. Okay, so I would explain more about the geometric meaning of these things, but let's start with the more computational approach. Okay, so at least it seems in kind of good cases, we have this relation. Although it's not always correct, we should discover exactly when this thing is correct. So in many cases, it seems this thing is true. Okay, so let's look at one example which we have in the book. Suppose f of x and y is equal to 3x y squared minus 2y plus 5x squared y squared. It says determine the value of f x y minus 1, 2. Okay, this means we should take first derivative with respect to x. So if we take derivative with respect to x of this function, we would get 3y squared minus 2y is going to be 0, and then plus 10 x y squared. And then we should take derivative with respect to y. It's going to be 6y plus 20 xy. Now the value of derivative at the points minus 1 and 2 is going to be 6 times 2 plus 20 times minus 1 times 2. It's going to be 12 minus 40, which is negative 28. Okay, so there are there are some ways to explain this thing. So I talked about the fact that if we take derivative with respect to y first, and then take derivative with respect to x, sometimes it's equal to the case where we take derivative with respect to x first, and then take derivative with respect to y. Well, is that always correct or sometimes correct? What are the conditions? Well, it's a question in the realm of pure mathematics. There are examples of functions which this thing is not correct. But first of all, as long as the functions in this course go, we always have this property. The point is that the functions, some functions are not, it's definitely always true for polynomials, that's correct. It's true for all the functions we know and we use. But sometimes in math, there are functions which are not, they are once differentiable and twice differentiable, but not, for example, 3 times differentiable. There are some very exotic functions. For those exotic functions, or maybe for functions defined on more exotic domains, these things might fail. But we wouldn't see that actually in this course. So we can look at even at a higher dimensional case. So is there a question from the previous slide? There is a question which I don't understand. It says fyxy question mark. If you explain more, I would answer that question. Okay, let's continue. So this is correct even in higher dimensional cases. So for example, in the book, we have this example of this function f of x, y, and z. This is a function from 3-dimensional space to R. It's defined to be y times e to the x plus ln of x times ln of z. Okay. Now, for example, here something you can see is that we can take, there are different ways we can take derivative. For example, we can take derivative with respect to x first. And then you might take derivative with respect to z. And then you might take derivative with respect to z again. It's going to be equal to take derivative with respect to z again, first, sorry, and then take derivative with respect to x, and then take derivative with respect to z. Or it would be the same as taking derivative with respect to z, and taking derivative with respect to z again, and taking derivative with respect to x. So it doesn't matter really in which order we are taking derivative. The only thing which matters is that we are taking derivative with respect to z twice, and derivative with respect to x once. That's what matters. So if I want to compute that, if I want to know what is this third order derivative, really it doesn't matter in which order I'm taking these derivatives. So for example, I can take derivative with respect to, say, z first. So derivative of f with respect to z would be, well, the first term is going to be 0. There is nothing, there's no z in the first term. And the derivative of the second thing, x, is a constant. I should take derivative just from the ln of z, which is 1 over z. So it's x over z. If I take derivative with respect to x second, so if I take derivative with respect to x of this thing, it would be just 1 over z, because it's the constant I'm multiplying x with that constant. And finally, if I take derivative with respect to z again, it would be minus 1 over z squared. And the order doesn't matter in the sense that if we would have tried, for example, this thing, we would have get the same answer. It really doesn't matter which order we are taking these derivatives. Okay. So it has a lot of application. These higher order derivatives, they have a lot of application. We would talk about those applications, but not in this section. We finished section 13.3. We would see more about higher order derivatives and how they help in so-called, well, when we want to find max and mean of a function, we use higher order derivatives to determine if these points are max or indeed they are mean or neither. Well, that was the question. David asked, how did you know you'd need to take derivative with respect to z twice and x once? That was the question. The question is asking, find, for example, this value. And I said, it really doesn't matter. You know, sometimes it's easier to change the order. So if for example, if you take here, so that's, first of all, that's the question. I'm asked to compute this thing. Also, sometimes it really makes sense to change the order. So if they ask me to compute this thing, I can, instead of that, I can compute this thing. Why? Because they are equal at the end, but it's easier. Because if you take first derivative with respect to x, you would get some term from this one, you would get some term from this one. But if you first take derivative with respect to z, the first term would vanish. So sometimes, even if they ask you, for example, take derivative of f with respect to x, then take derivative with respect to y, then take derivative with respect to z, you might feel it would simplify computations if you first take derivative with respect to y, for example, then take derivative with respect to z, and then take derivative with respect to x. If that's the case, you should do that. Sometimes it would really simplify things. And I really can assume, I can imagine there would be a case where I ask you to compute this, and you wouldn't really be able to compute derivative of f with respect to x. It might be so hard that you can't compute that. But as soon as you recognize you can change the order, if you first take derivative with respect to y, it would be a lot easier, and you can compute the right-hand side quantity. And because they're equal, you're allowed to do that. Okay. Okay, we would see more examples. Well, actually, finding an example of what I just said is quite simple. I like you to think about that. Actually, it's better than I telling you some example. You can write down a function f, x, y, z. That's a good thing to think about. Such that taking derivative with respect to x, taking derivative with respect to y, and taking derivative with respect to z would be very hard for you to compute. For example, it's almost impossible for you to compute. But if you change the order, for example, in this way, you can compute the answer quite simply. It's a good question. It's a good question to find such an examples. I can write an example instantly, but I would like you to think about it, to come up with an example yourself. I would mention some of these examples actually in the homework. Anyway, let's start the new section, differentials. Okay. So as you remember in single variable calculus, which by single variable calculus, I mean the kind of calculus we used to study before this course, the calculus with just one variable. When we had functions of this form, y equals f of x, like x squared, sine of x, ln of x, all these things. When we wanted to work with integrals, we used to have things like this: integral of, say, f of x dx. And it might always be a little confusing, what does that dx really mean? So dx is a notation. For example, dx, dy, etc. And its meaning is a little vague, especially in calculus. But there are things, although we don't understand these things correctly, what is this dx, for example, here? Is it a function? Is it a variable? What is this thing? So although it's a little bit vague here in this course, what this thing really mean, but there are things we know. For example, dy here, using this equation, y equals f of x, dy actually is equal to f prime of x dx. We had such a relation. So for example, we use this thing when we are doing change of variable in an integral. So we have a similar thing in higher dimension too. We have similar thing in functions of several variables. So for example, if I have a function of two variables, say x and y, and if I set this function to be equal to z, there is a notion of, say, dz, or there is a notion of dy, or there is a notion of dx. But the relation between these things is slightly more complicated. And it is very important. So actually the relation which is correct between these things is what I'm going to write now. dz is equal to partial derivative of f with respect to x times dx plus partial derivative of f with respect to y dy. So at this point, this thing is completely something notational with us. There is no real meaning for us at this point behind dx, dy, and dz. They are just, in some sense, we want to think about them as dx is something like delta x, very small change in x, very small change in dy is something like very small change in y. That's what I mean by delta x. Very small change in y. Or delta z, very small change in z. But that's not exactly correct, and it's quite hard actually to make complete sense of that. So it is better to start just computationally, and through time we will understand what it really means. So for example, if you have a three-dimensional example, say f of x, y, and z, we have such a function. I can define that to be equal to w. dw would be equal to partial derivative of f with respect to x dx plus partial derivative of f with respect to y dy plus partial derivative of f with respect to z dz. Well, let's look at an example. So, for example, if z is equal to 2x cosine of y minus x squared y squared. So, if the question is find dz, what is dz? I should say dz is equal to partial derivative of f with respect to x dx plus partial derivative of f with respect to y dy. So partial derivative of this z is actually equal to f of x and y, right? If I compute its partial derivative with respect to x, what I'm going to get. So partial derivative of this function with respect to x is going to be 2 cosine of y. Cosine of y is the constant coefficient of x. Here I also have 2 minus 2xy squared dx plus. Now I should compute the partial derivative with respect to y. I continue below here. The partial derivative with respect to y. Well, cosine of y is, its derivative is minus sine of y. We have 2x as a constant coefficient 2. And then derivative of the second term is 2x squared y dy. So that's going to be, that's the definition of the z here. Okay. Now, we use these differentials both in derivative and integral. So just have that in mind, how we compute dx, dy, dz, dw, and things like that. Okay, so there is a very similar, very similar thing. So if I have a function, say f of x and y equal to z, it means the domain is something subset of R2, right? The domain is something two-dimensional. X and y are in the domain. F is a function from R2 to R. So the input comes from R2. So say this is R2, the plane. And the target or codomain is R. And F is a function from R2 to R. Okay. Now suppose I'm at the points X and Y. Now the question is, if I change X a little bit, if I move to a nearby point, say if I go to a point X, say we are at the point X1, Y1. If I move to a new point, which the Y coordinate is the same, but the first coordinate changes to X2, the value of F might change slightly. So, and suppose these 2 points are very close to each other. So from a point X1, Y1, I'm moving to a second point, X2 and Y1, okay? So I'm changing the value of X in the domain slightly. If I go from X1 to X2, and if they are very close to each other, I would expect that the value of the function at these 2 points are very close to each other. So for example, f of x1, y1 is here. F of x to y2 is x to y1 is a nearby point. Okay, so I might wonder what's the distance between these two things? What is the change of the value of f? Okay, or I might look at the domain and I might look at the point x1, y1 here. And I might change the value of y a little bit. So suppose I'm moving to a second point, which the value of x1 is the same, but the value of y1 changes to y2. I move to a new point, but it's a very close point. It's a nearby point. Now, if I look at the value of the function f at the first point, f of x1, y1, and the second point, f of x1, y2, if these 2 points are close in the domain, I would expect the value of the function at these 2 points to be close to each other too. Anyway, the question we might want to ask is that how much the value of the function f would change if we change x or y a little bit, okay? So for example, suppose z is equal to f of x and y. And if we change x to a nearby point, x plus delta x, which delta x is a small change. So if we replace x with x plus delta x, or if we replace y with y plus delta y, where delta y is, again, it's a small change. How much does it affect the value of f? Like if we have f equal to f of x and y, now f would be x plus delta x and y plus delta y. How much it's going to change the value of the function f? So let's look at an explicit example to understand what it means. It wouldn't change much, but we want to able to understand how exactly how much, right? So for example, look at this function. X, say x squared plus y. Suppose we are looking at this function at the point x and y equal to 2 and 3. Okay, the value of the function at this point 2 and 3 is equal to 2 squared plus 3, which is 4, plus 3, which is 7. Okay, now suppose I'm changing x a little bit. Suppose I'm going to change by a very small amount. I don't know, say 0.1. Okay, so I'm moving from the point 2 and 3, I'm moving to a new point, 2 plus 0.1 and 3, which is 2.1 and 3. Okay, it's a very nearby point. How much it's going to affect the value of f? F at this new point, 2.1 and 3, is equal to 2.1 squared plus 3. Okay, what is 2.1 squared? 2.1 squared. It's equal to 4.41 plus 3. It's 7.41. So the amount of change we would see in the value of f, how much it has changed, is 0.41. That's how much it has changed, right? Now let's change y with the same value. So rather than changing the value of x with this amount, 0.1, let's change the value of y. Let's replace 3 by 3.1. So it would be the value of the function would be equal to 2 squared plus 3.1, which is 4 plus 3.1, which is equal to 7.1. So how much it affected f? It's just 0.1. So it seems if we change x, it would affect the function more than changing y. So changing x affect f more than changing y. Now, what is the reason? Why here f is more, it's like f depends more on the change of x rather than change of y. Why is that? Okay, so that's the question. Yes, that is true. It's because, well, we have the order of x here is 2. The order of y here is actually 1. When we don't write it, it's just 1. Okay. But what if it wasn't a polynomial? What if rather than something like this, we had slightly more complicated function, f of x and y? What if we had x squared y plus cosine of x, say y squared? How can we decide how up to what extent f is dependent on these two variables x and y, and how much they would affect the function f if we change x and y? Actually, the answer is partial derivative of f with respect to x shows how much f depends on the change of y. And partial derivative of f with respect to y shows how much it depends on y. So if we look at the previous question, here we can say the derivative of f with respect to x is 2x. And at this point, 2 and 3, 2x is equal to 4. X is equal to 2, right? But derivative of f with respect to y is equal to 1. It shows f is affected more with if we change x rather than if we change y. The derivative, the partial derivatives, they show us how much the value of the function depends on something. So here, for example, if we are at the point x and y.
So the larger the partial derivative, the more change that, the more.
Yes, that is true. So let's look at one more example. So suppose here we have this function f here, and we are looking at a point in the domain 1 and 2, and we want to see how much f is affected by the change of x and y. So in order to understand that, we should take derivatives of f with respect to x and y, and that would show us if f would be more affected by the change of x or y. So here the partial derivative with respect to x is 2xy. Partial derivative of cosine of x is minus sine of x and y. Maybe a better example is, sorry, let's take the point 0 and 2, because I don't know what is sine of 1. So it would be, here it would be 0. You see, x is 0, sine of x is 0. It does not mean if we change x, the function wouldn't change. Because here you might say the derivative of f with respect to x is 0. So it probably means if we change x, f wouldn't change. No, it does not mean that. So that's very important. It does not mean f is not affected by the change of x. But actually it means something close to that. It means it would change a lot slower than if the derivative wasn't 0. So what it means is that it's affected very little, let's say like that. Okay, what about the derivative with respect to y? We would get x squared plus 2 cosine of x y squared, y. So at that point, it would be 0 squared plus 2 cosine of 0 times 2, which is 4. So it depends a lot more on the change of y rather than change of x. If you change y, it would affect the function a lot more than changing x. Okay. That's what it means. So a little more, if we want to study this problem a little more systematically, actually, if I define the function f of x and y, if I let this function to be equal to z, the question is if I replace x with a nearby number, say x plus delta x, where, as I mentioned earlier, this delta x is a very small change. So suppose in your mind, you can assume it's 0.1 or something even smaller. And if I replace y with y plus delta y, it would affect the function f. So, and therefore it would affect z. So that would cause z to change to a new value. Let's show it with z plus delta z. So if z is equal to f of x and y, z plus delta z is equal to, suppose this is equal to f of x plus delta x and y plus delta y. Okay, I would define delta z to z plus delta z to be this new number. And the question is how can I compute delta z? How can I see how much this thing would change? This exactly follows the rule we had for differential. So delta z is going to be equal to derivative of f with respect to x, delta x, plus derivative of f with respect to y, delta y, plus some very, very small error, which we would kind of neglect this small error usually. What is that small error? Well, I think it's better at this point not to mention what is that error, but just remember there's a small error. We show it with epsilon, just to say it is a small. So for example, in the previous question here, we had f of x and y was equal to x squared plus y plus cosine of x y squared. Okay, and we were looking at this point 0 and 2. And I want to see if I change the point 0 and 2 to a very nearby point, 0 plus delta x and 2 plus delta y, what would be the value of the function? So what is f of 0 plus delta x and 2 plus delta y? This formula I just wrote tells us this is going to be equal to partial derivative of f with respect to x delta x plus partial derivative of f with respect to y delta y plus a very small error. Okay, so partial derivative of f with respect to x is equal to 2xy minus sine of x y squared delta x plus partial derivative of f with respect to y is equal to x squared plus 2 cosine of x y delta y plus epsilon. Now here we are at this point where x is 0 and y is 2. If we replace them, we get 0 here, delta x plus 4 delta y plus epsilon. So the answer is 4 delta y plus epsilon. So f at a nearby point to 0 and 2 would be equal to 4 delta y plus epsilon. So it seems it almost doesn't depend on x. It depends on x. As we can see, we only see delta y here. So it depends on x, but how much it depends on x would appear in this epsilon, which is very, very small. What we say is that up to first order, it doesn't depend on x. So if they tell us study the first order approximation of f, it means we should only look at this thing here. Okay. Actually, this is quite useful in approximating a function. Okay, so this is quite interesting. So suppose, I would first mention a single variable case. Suppose we have f of x equal to square root of x, okay? And suppose they ask us to compute f of, say, 9.01. And suppose we don't have calculator. Suppose we want to compute this thing, and suppose we don't have a calculator, okay? So I can't directly compute the square root of 9.01, right? I can't do that. I don't know what is that. But what I know is that this point 9.01 is very, very close to 9. And I know what is the square root of 9. It's 3, okay? I can exploit this fact. So here y is equal to square root of x. What I want to know in our new language is that if we replace 9 with 9 plus, say, well here actually, let me first write it like that. What I want to know is that if I replace x with x plus delta x, what would happen to y? Y would become y plus delta y. And this y plus delta y is what I'm looking for now. Okay, so y plus delta y is f of x plus delta x. Okay, so here I know that f of 9 is equal to 3, right? This is the value of x, 9. This is the value of y, 3. What is delta x? Delta x is the amount I'm changing x. Here it's 0.01. And what I'm looking for is this delta y. What is this delta y? Well, delta y is derivative of f with respect to x, delta x. In the higher dimensional cases, we would continue this thing. In one dimensional case, there is no continuation. That's just it. Okay. So what is derivative of f with respect to x? We should take derivative of this function. It's 1 over 2 squared root of x, delta x. Okay. So 1 over squared root of 9, and delta x is 0.01. This is equal to 0.01 over, well, square root of 9 is 3. 2 times 3 is 6. Well, this is supposed to be change in the value of f. It means that this function f of 9.01, which is actually square root of 9.01, is equal to 3 plus this small change, 0.01 over 6. So that's the way to, that's true approximately. That's an approximation. So that's a way to approximate functions if we can't compute them directly. But if we know a nearby point, the value at the nearby point. So let's look at one more example, a similar example. Suppose we have f of x and y equal to z. Suppose f is equal to square root of 4 minus x squared minus y squared. Someone has asked why it's an only approximation and not the exact value. The reason is here. Delta z is equal to partial derivative of f with respect to x delta x plus partial derivative of f with respect to y delta y plus a very small error. We have this error in the other cases too. So whenever we write this formula, there is a small error at the end there. We are not taking that part into the account. So here, for example, suppose we know what is the value of the function. Yeah, another question is that would it be exact if the change in x or y is 0? Well, if the change in both of them is 0, yes. But if you change only one of them by 0 and the other one by non-zero number, no. So let's look at this one. Suppose we are asked to compute f of 1.01 and 0.97. The question is find this thing. Well, I mean, it's pretty hard to compute that without calculator, but we know we can compute something very close to that. So there is a very nearby point. That's 1 and 1, right? So I would define x to be 1. I would define y to be 1. What is delta x, the small change? Well, here it's, in the first case, it's 0.01. In the second case, what is the change in the second case? What is the change in the value of y? Can anyone tell me what is that? Not exactly. Yeah, that's true. Now, the change is negative here. You see, we subtracted 1 by this number to get this new thing. So the change is negative. So the change is positive in the first case and it's negative in the second case. And that's very important. Okay, I can compute f of 1 and 1. Is it even a good point, f of 1 and 1? Maybe it was better rather than 4, I choose here 6. Okay, I can compute f of 1 and 1. It would be 6 minus 1 minus 1. It's the square root of 4. It is equal to 2. That's easy. Now I want to compute this f of the function at this point. I want to be able to approximate this function at this point. And that might be quite complicated. If we don't have this technique of derivative, we can't really do that. I mean, we should have computed 6 minus 1.01 squared minus 0.97 squared. And who can really compute a radical like that, right? So it's not easy to do that. But this new technique, we know it might help us. So change in the value of z is equal to partial derivative of f with respect to x, change in the value of x, plus partial derivative of f with respect to y, change in the value of y, delta x, delta y. Okay, what is derivative of this function with respect to x? So I should take derivative of what I have inside first with respect to x. It would be minus 2x over 2 times this radical here I have, 6 minus x squared minus y squared. That would be the derivative with respect to x times delta x plus. Now, partial derivative of this function with respect to y. Again, I should take derivative with respect to y of what I have inside. It would be minus 2y over 2 times this radical itself, delta y. Okay, at the point 1, 1, this is equal to minus 1 over square root of 5 delta x. What is delta x? Delta x is 0.01 plus minus 1 over, again, square root of, square root of 4. Over square root of 4 times delta y. What is delta y? Delta y is negative 0.03. Okay, delta 4 is 2, so I can write here 2, and here I can write 2. So here I have minus 0.005 plus 0.0015. So this is the total thing I have, and then the result would be minus 0.0045. Hopefully it is correct. That would be the change of value. Extra zero where? Yeah, I see. Is that correct? Let me check it for a second. Okay, is there any problem up to this point? Do you see? I think it's correct.
Isn't it 0.01? Because you're
Where?
Because the 0.005 is negative and your 0.015 is positive.
Say again, where are you referring to?
The answer, it's negative 0.005 plus 0.015. So isn't that 0.01 as your answer?
Oh, yeah. No, I'm checking to make sure up to this point I haven't made.
Oh, okay, gotcha. Sorry.
Yeah. Okay. Okay, it seems to be correct. So that would be the change in the value of y, and the change is positive. Note that the final thing is positive. So f of this point, 1.01, 0.97, is going to be f of 1 and 1, which is 2, plus this change, which is 0.01, which is 2.01. So that's an approximation again. So we have a good approximation for the f at this point. This thing, because we are only look at the first derivative to do this approximation, we are just looking at the first derivative to do this approximation. We can look at, you see, if we want to find a better approximation, there are ways to look at higher derivatives. Here we are just looking at the first, we just took one partial derivative, right? Because of that, this approximation is called linear approximation. And this is the most important kind of approximation in economics or engineering or physics or anything, anywhere else, linear approximation. This kind of approximation is called linear approximation. So we have that one-dimensional case here, and we have the two-dimensional case here. This is two-dimensional linear approximation. Okay. Let's look at one more example. Suppose we have a function, say, z is equal to sine of x times cosine of y. And suppose we want to compute, this is, this is f of x and y is equal to sine of x and cosine of y. And suppose we want to compute f of pi over 6 plus pi over 100 and pi over 3 plus pi over 200. And we want to approximate this thing. So I would give you maybe 2 minutes to find this approximation. What is the value of sine of pi over 6 plus pi over 100 times cosine of pi over 3 plus pi over 200 approximately? And I should also say this is the notation for approximately. It doesn't mean it is equal to, it means it is equal to, it's almost equal to something. It's an approximation. Okay, think about it for a few minutes. Okay, does anyone have the answer? One over 4 minus pi times radical 3 over 400. And then we have a more 0.0068, 0.511. Well, I just want one answer, right? The final answer. Okay, let's see. So first, let's compute z at this nearby point. Let's first compute z of pi over 6 and pi over 3. This is a nearby point, which we can compute the value of the function there. It would be sine of pi over 6, cosine of pi over 3. And it's 1 over 2, sine of pi over 6 is 1 over 2, cosine of pi over 3 is 1 over 3. The result is 1 over 6. Okay, we have that. Now we want to see if we replace these points x and y, this point x and y, by a nearby point, how much the value of the function would change. The change in the value of the function, delta z, is equal to partial derivative of the function with respect to x times the change in x plus the change, well, partial derivative of function with respect to y times the change in y. Okay, what is derivative of function with respect to x? I should take derivative of sine of x, it's cosine of x. And then we have cosine of y there times delta x plus, I should take now partial derivative of the function with respect to y. Derivative of cosine would be minus sine of y. So we have sine of x, sine of y times change in y, delta y. Okay, so this is equal to cosine of x, cosine of y, delta x. So x and y are pi over 3. So it's cosine of pi over 3 times cosine of pi over 3. So it would be 1 over square root of 3 over 2 times 1 over 2 times delta x. Delta x here is pi over 100 minus sine of x is 1 over 2. Sine of y is the square root of 3 over 2. Delta y is pi over 200. Okay, so here we would get square root of 3 over 4, pi over 100 minus pi over 200. If we multiply them, we would get pi over 200. Finally, we get square root of 3 phi over square root of 3 pi over 800. That's the change in z, and it's positive. It means the value of the function at this nearby point is almost equal to 1 over 6 plus this square root of 3 pi over 800. Okay. Okay, so here we have the answer. Is there any question here? What do you mean by NOY 1 over 4? Cosine of pi over 3 is equal to 1 over 2. That is correct. So I'm not sure. Do you have a question or you're writing an answer to something? I made a mistake. Where are you referring? Oh, here. Oh, you're saying here it's 1 over 4. Oh, I thought I am writing 1 over 4. That's very strange. Okay, thank you. Do I have a mistake anywhere else? No, I think that's it. Okay, thank you. So yeah, so we can look at one more example, or we can continue. I think, okay, we can continue to a very, very related subject, very related topic. So here we're thinking about how much the value of the function would change. Another way of thinking about what we have here is so-called error analysis. So sometimes, you know, in reality, the variables are not really fixed. You can't control every variable. So for example, so there's a very simple example in the book. It's good to understand the topic. Suppose we have a box. Okay. And suppose each side, suppose I show this side with X, this side with Y, or maybe this side with Y and this side with Z. Okay, I have a box here. The volume of the box is equal to X, Y, Z. So I can think about it as actually the function F. So let's show this thing with W, supposed to be F of X and Y and Z equal to X, Y, Z. So F is a function which computes the value of the volume of the box. Okay. So for example, if X is, say, I don't know, say X is 1, Y is 2, Z is 3, the volume of the box would be F of 1, 2, 3, which is simply the multiplication of these numbers, which is 6, right? But in reality, if we are to really construct a box, we can't always really make each side exactly equal to these numbers, right? In reality, there would be always some error in these constructions, right? In the length of these sides. And of course, if you were to construct a real box, it wouldn't be exactly equal to 1 or exactly equal to 2. So there would be some error. So suppose we are, the people who are making this box, they might make mistake, but there is a bound on the error they might do. So suppose the possible error, so suppose the possible error involved in like making this this box is plus minus 0.1, which means X might be 1, it might be 1.1, or it might be 1 minus 0.1, which is 0.9, or anything in between. X can be anything in between. You might have seen when you buy something, sometimes it's the like the weight is written a number, so say 500 plus or minus something. That means there might be a mistake in measuring. There might be an error. Okay. Now in the values of X, Y, and Z, there might be an error up to, the error can be something up to at most plus or minus 0.1. Okay. There are two kinds of, you know, when we are like measuring things, when we are constructing things, there are two kinds of error. One is just simply the error itself. The other one is something called relative error. I want to mention these two concepts in this example. So what is each of them? So what is the error? The error is exactly what we talked about. The error is if we here we have W equals say F of X, Y, and Z. Here we have delta X equal delta Y equal delta Z equal to say plus or minus 0.1. Error is simply delta W. Okay, that's simply the error. But there is something else called relative error. And that's equal to delta W over W. That's the relative mistake we might have. So let's look at this example we had. Here we had volume equal to XYZ, right? And the volume at that point was 6. The volume of the box is 6. However, we are not sure x is equal to 1. X might be 1 plus or minus this number here. Y might be 2 plus or minus this number. Z might be plus or minus this number. So we are not exactly sure about our measurements, right? What we should do here is we should say change in V, delta V is equal to derivative of V with respect to X delta X plus derivative of Y, V with respect to Y delta Y plus derivative of V with respect to Z delta Z. Okay, and we should compute this thing. This is going to be the error. So to change the derivative of V with respect to X is YZ times delta X. Derivative of V, the volume with respect to Y is XZ. By V, I mean volume. It's the initial, the first letter of volume. Derivative of V with respect to Y is XZ times delta Y. Derivative of V with respect to Z is XY delta Z. Okay, so now it's quite interesting here. What is the amount we should assume for delta X, delta Y, delta Z? Should we try plus 0.1 or minus 0.1? Well, we should, when we are, it's something which is always true. If you are doing engineering things or economics or whatever, when you're thinking about the amount of mistake or error you might have in your computation, you should always consider the worst case. Worst case scenario. So here, YZ is equal to, well, 6 times delta X. Delta X might be plus or minus 0.1 plus. XZ is equal to 1.2, it's 2 times plus or minus. Delta Y is also that amount. Plus XY, XY is also, well, X is 3, sorry. It's 2 times plus or minus 0.1. Now, well, so it would be 0.1 plus or minus times the sum of these numbers, 6 plus 3 plus 2, which is 11. So the potential mistake, like error we might have is plus or minus 1.1. This thing is the error in the volume of the box. Okay, what is the relative error? The relative error is delta V here, which is plus or minus 1.1 over the volume here, which is 6. That's the relative error. So what does the relative error mean? Well, it means when we divide by the volume of the box, it shows if the volume is greater, that is a large number, small error doesn't matter anymore. So for example, if the volume of the box is 6, this much error might be significant. But if, for example, the volume, if we had another box, which its volume was 100, if we had the same amount of error, it wouldn't be important error because this ratio would have been very small. So this ratio in some sense shows how much this error really matters to us. Okay, so one way to get a feeling about it is to, if we multiply it by 100, we got the percentage of the error, right? What is the ratio of the error? Here is 1.1 over 6 times 100. It's 18%, almost 18%. So here we have 18% error in this. That's the amount of relative error. If we express it in terms of percent, if they say we have like 18% error, that's what really means. It's relative error, multiplying it by 100, we get the relative error. So that's one thing to understand. So if you have a box which is volume is 6 and your error is 1.1, that's 18% error. If you have a box which is volume says 100 and you have so suppose you have another box which its volume is 100, but the error you have is same amount of error. Now the error is the same, but the relative error is a lot smaller because, well, if the volume of the box is 100, we might not really care about this small number. This number is very small relative to 100, although it's not small relative to 6, right? So here, if we divide 100 by 100, we see the relative error is 1.1%. So the relative error would be a lot smaller. Okay, any question? Okay, let me finish this section with an important theorem. Suppose we have a function of 2 variable, or a function of 3 variable, or even more. I mean, the number of variables really doesn't matter. If the function f is, if it's differentiable, which means it has derivative. If we have a function which is differentiable, which means we can take derivative of, it means the function is also continuous. Does anyone know any example of a function which is not differentiable? Let's see. Do you know any example of a function which it doesn't have derivative at a point? Okay, I would write an example. So for single valued functions, look at this function, the absolute value of x. Yeah, that's correct. If you look at its graph, it looks like this. You see here, it's very pointy here. You see there is a singular point, it's very pointy there. These functions, whenever they have these broken points, they are not differentiable. There is no derivative there. The square root of x is differentiable in its domain. Square root of x, we know what is derivative of square root of x, right? Derivative of square root of x is 1 over 2 square root of x. But whenever they are, well, I mean, it has derivative at 0. It's another thing, but derivative of x looks like this. Well, at 0 it's infinity. You are right. So okay, I understand what you're saying now. Yeah, it's the derivative at 0. It has one. Well, we can define only so-called the right derivative, and the right derivative at 0 is infinity. So you're right. Yeah, that is true. Thank you. So another example is absolute value of x, which, as you can see, is broken. When we have a function which is broken like this, has broken points, is not differentiable. So for example, for higher order terms, it's if we want to have a higher dimensional example, this function is an example of a function which is not differentiable. If we look at we can look at the graph of this function maybe. Let me show you to see this thing is also let me show you this thing is let me show you this thing is also a broken function. Let's see. So let me see how can we have the absolute value? Where is the absolute value? Well, hopefully it has absolute value, right? Let's see. Maybe it would understand it like this. Oh, yeah. So the function would look like this. Let's make it a little more. So as you can see, do you see these edges here we have? Do you see these sharp edges? The function is not differentiable even on these edges. And of course, the function is not differentiable at that point 0 and 0. As you can see, there is a kind of sharp, pointy point there. It's not differentiable at that point too. So whenever we have these kind of broken points, the edgy points, the pointy things, the function is not differentiable at these points. So it's an example of, so whenever the function is smooth, it's kind of being differentiable means the function is smooth. There is no edgy things. There is no edge, there is no such points. Okay, so that's what we mean by a differentiable function. This is an example of a function which is not differentiable. It's not differentiable on the edge. Okay, so I guess here we have it. Yep, that's this section. We should start now section 13.5, which is about chain rule, which is quite important. So we can have a little break. Let's say, let's have 10-minute break. Let's continue at 10:35 with the section 13.5. Is there any question? Okay, if not, yep. Is there a question?
I have a question.
Yeah.
Could you go over question 3.1.4 in the homework?
Oh, yeah, sure.
Thank you.
Yeah. .1.4.
Yeah, it's the one with the log.
Yeah, okay. So the question is find the domain of log of x minus 1 over x plus y. So, okay, here you should say three things. One is that x plus y here is a denominator, so x plus y should be non-zero. The second thing is that we are taking derivative of x minus y over x plus y. So the whole thing, x minus y over x plus y should be positive. And the third thing is that the whole log is under radical. So log of x minus y over x plus y should be positive. We should solve these two inequalities and, well, the first one, and then take intersection of the answers. Is any of them, which one is confusing, or which one is the one you have question about?
What is, could you explain number 2?
Yeah, so I mean, when we have a fraction like a over b, it is positive if and only if a and b have the same sign, you know. Like 2 over 4 is positive, minus 2 over minus 4 is also positive, because we can cancel minus 2 with the negative sign with the negative sign. So whenever we have a fraction, if it's positive, it means a and b here, they have the same sign. So x minus y and x plus y, they should have the same sign. Now, you might remember we had a way of understanding, analyzing the sign of these things. So if you have x minus y and x plus y, either both of them, maybe it's better to write it directly. So either both of them should be positive, or Both of them should be negative. Does it make sense? If I want the fraction to be positive, either both numerator and denominator should be positive, or both numerator and denominator should be negative.
Yeah, it makes sense.
Okay.
Are you supposed
So,
to?
yeah.
Are you supposed to draw?
Actually, we should continue, but I mean, it's not done yet. So
Okay.
we need to continue here to analyze these things more, but it's part of the answer.
Are we supposed to draw those tables that we did in class? Because I thought that was only for one variable functions.
Well, I mean, yeah, we have, no, I don't expect you to do that, although it is possible, but no, I don't expect you to do that here. You can do it directly. So here, for example, you see, let's number them 1, 2, 3, 4. For example, here 1 says actually just says x should be greater than y. 2 says x should be greater than minus y, okay? Now, if you look at R2, x equal to y is this line. X equals to minus y is the other line. Okay, now we should, maybe it's better just to sketch one of them. So here x is equal to y. On one side, x is less than y. On the other side, x is greater than y. Does anyone know which side x is greater than y and which side x is less than y? Anyone? So actually on the right side, x is greater than y, and on the left side, x is less than y. So when we have x greater than y, it means this area. And then we have another line, x equal to minus y. On one side of it, x is greater than minus y. On one side, x is less than minus y. So again here, which side do we have x is greater than minus 1? So actually, again, this side. Now, the intersection of these two is, the intersection of these two is this. So for example, the answer to this thing is this area. Okay. The answer to this one, you can do the same thing to see the answer to the other case, to this case, is this area. And because we have or between them, it means either we should be here or here, and not here and not here. So for example, that's one way to analyze this one. We should do the same thing for others. For example, for same thing for 3.
Would you expect us to draw the graph that you just drew, or is that just for like personal reference?
It's better to draw the graph because it would be very hard to do it without the graph.
So should we draw graphs for all problems in question 3?
Well, well, some of them you can, it's better to do it, definitely. I mean, that's the clearest way to show what is the domain of the function. But some of them you might be able to do it without sketching the graph. For example, maybe 3.1.5 doesn't really need it. So I would leave it to your judgment that if it's necessary, if you can explain it without sketching the graph, if you really can do it, it's okay. But it might be pretty hard to do that. So I would leave it to your judgment if it's necessary or not in each case.
Okay.
Okay.
Also, I'm not sure if I wrote my answer. My final answer, I wrote it in a certain notation. I'm gonna try and send it to you through the chat function.
Okay.
Hold on.